And we're back. Today, we will talk about the final project with a little bit of refresher material concerning issues that you will be examining for the final project. But before we begin, let's go over a little bit of administrative bit. The final project will be due the 8th of May, which is a Friday at 8 p.m. Now, on the academic calendar, that's when dormitories close. It's the last day of finals, and I thought it'd be a good time to have this material due. I don't want to make the homework due, the final project rather, due too far into a Friday night, because I'm sure you're all itching to enjoy your first Friday night outside of the semester. And so the final project, as discussed before, will consist of two components. One will be the actual work of the project, and it will also consist of a presentation. And so we'll be doing the presentation during the scheduled final exam period, and that was already predetermined by the registrar. I don't have any control over it. I'm not excited about 8 o'clock in the morning. I'm sure you aren't either. But on Monday, the 4th of May, at 8 a.m., that's when your slides will be due, and each of you will be giving an 8-minute presentation during that time period for class. So please make sure you have your slides in so that I can assign you a grade for your presentations. And so all submissions for this will be on the Blackboard, so please do not wait until the last minute, and do not email me anything. My email cannot accommodate all of these projects. And when you submit your final project, kindly put it in a zip file archive and then put that on cloud storage. Everyone has access to Microsoft OneDrive. I know some of you use Google Drive, some of you use Dropbox, but please produce a zip file for your final project submission. And then when you do the submission on the 8th of May by 8 p.m., please submit a link to that zip file that you've linked onto cloud storage so I can then subsequently download it and then go through all of that. All right, so it was then that you realize that today is the last class. Whether that's good news or bad news, well, that's really up to you. And so we made it. This is the last class. You don't have to hear me talk about this stuff. Either way, I hope that all of this material has benefited you and you have learned something and it will advantage you in your future careers or in graduate school, should you choose to go on to graduate school directly, and I certainly hope that many of you do that. So we talked about during the semester color space, and we talked in particular about RGB, and we said it's a representation for colors in an image, and each coordinate of this color cube represents some mixture of red, green, and blue to correspond to a certain color, and I've depicted the color cube here. And so data structure-wise, we represent an image as a mixture of colors, and that's an M by N pixel image. But that third dimension, the 3, is the set of so-called color channels, where the first slice of that M by N by 3 cube or rectangular solid is the red channel. The next slice is the green channel, and the next slice is the blue channel, and we experimented during the semester with that in MATLAB. And so that was the data structure for an image when you read it in color image, when you read it into MATLAB using IMRead, which is part of the computer vision image processing toolbox. And so we also talked about so-called appearance-based features. And here we have on the left-hand side an image of a building, and on the right-hand side an image of a field of sunflowers. And so with this appearance-based representation, we represented two things. We represented the color, and we represented the shape. So here we have a depiction of color representation portion of appearance-based features. And so here we take the red, green, and blue channel for this color image for the building on the left-hand side. We compute the histogram of the red channel, the green channel, and the blue channel, and each of those histograms has 10 bins. We concatenate together those 10 bins to form a single 30 vector, which is the color associated with that image of the building. So we do the same thing with the sunflower fields, and because the sunflower fields consist of different colors, more yellows, more blue sky, different colored green for the leaves, we get a different set of histograms for these RGB color channels or color planes for this sunflower image. We then compute the histograms for each of these color channels, red, green, and blue, for using 10 bins each. It gives us another single 30 vector. And so this 30 vector represents the color of the sunflowers, and then on the left-hand side, this 30 vector represents the color information for the building image. And so we also talked about edges, and with this edges, we developed this idea of the central difference, which was an implementation, a discrete implementation of the derivative. And we took that derivative over the image, treating it as a relief map using a so-called convolution mask. And so that mask contained some coefficients that implemented the so-called central difference. And then we took that mask, slide it across, and that gives us the resulting slope at the so-called center pixel. And so we needed more than the slope at more than one pixel, one slope point, in order to form a line, because a line is more than 1 point. And so we did that 3 times to have 3 edge points, which we then used to describe our edge line. And so this is a gradient at 3 different places, and we generalize this using a mask, and we can compute with this mask the derivative along the x direction in the image or the derivative along the y direction in the image. And so this gives us the slope with respect to horizontal and vertical direction. And so we can also place emphasis on the center, and depending on how we choose our values for this 3x3 convolution mask, we get either the Sobel or the canny edge detection. So we take these gradients along x and y, we can combine them, taking the magnitude to give us the magnitude of the edge, and then we can also take the inverse tan of the derivative, the gradient with respect to y over x, the gradient with respect to x, and that gives us the edge orientation. So now from this edge response from this convolution mask, representing the partial derivative of the intensity of the surface with respect to x and y, we can get the edge magnitude as well as the edge orientation or the edge direction. And so now we can take this edge description to describe shape. And when we looked at or thought of the building image, well, we have a lot of horizontal edges and a lot of vertical edges. So then if we extract all that edge information and then we compute the histogram with 10 bins, we're going to get some peaks at 90 degrees and 180 degrees, representing all those prominent edges in this engineered structure. So if we do that, we get a 10 vector if we use 10 bins for the histogram over the edge orientation or edge angles, and this gives us a representation of the shape for this image of the building. We do the same thing, similar fashion, to the sunflower image, and this has a different set of edges. It has a lot of rounded surfaces, so we're going to get more of a uniform distribution over the set of edge angles. And so we take that histogram, it's going to be a little bit flatter, a lot flatter than the building, rather than being peaked bimodally at 90 degrees and 180 degrees. We do that histogram with 10 bins, and we get a 10 vector, resulting in a shape description for that sunflower image. And so we can extract a color representation, we can extract a shape representation, and we concatenate those 30 color features as we described before with the 10 shape features, and that gives us a 40 vector, a vector of rank 40, which is our appearance-based representation. We do the same thing with the sunflower, and we get, again, our 40 vector, which is the appearance-based representation of our sunflower image. So mathematically, we have each image. Maybe this is the first image, x1, and this is the second image, vector value x2. Well, the rank of x1, x2 is 40 because they both consist of 40 dimensions or 40 features in the representation. And so here, the ith image, mathematically we represent, regardless of which image it is in our data set, the first, the second, the third, and so forth. Here we represent a vector xi as consisting of the first feature, second feature, up to and including the 40th feature in this example, which is xi, 40. Okay, so this is our representation, and we will talk about the task for our final project. And so your task is to implement image clustering. And you might be asking, well, why is this useful? Let me tell you. So back in the old days, way back when, I remember when I was a kid, you had film cameras, and they were really nice cameras, SLR single lens reflex cameras, and you would buy film for maybe $5 to $7 for a roll for 24 exposures. Maybe if you got it on sale, you'd get 32 exposures. And then you put this thing in the camera, and you'd snap your pictures, and then you'd take this film, rewind it back into the canister, bring it to a drugstore to get it developed, and that would cost you another $7 or so when I was a kid. It's a lot more expensive now. And then you'd get mail, go back and pick up your envelope of your negatives as well as your prints. And then you take these prints, put them in a photo album, and you would collect photo albums, a whole bunch of them over time. So this is what used to happen, and now the advent of digital cameras has made photography much more prolific, more commonplace, especially when you have now these phones, these cell phones that have smartphones with cameras, cell phone cameras. And so now you take much more images, much more pictures. When it was back in the days of film camera, you would kind of hold your shot because it was more expensive when you include the cost of the film as well as the cost of the processing to get the prints made. It was a lot more expensive to take a photograph, and so you wouldn't just willy-nilly take a photo of everything, hundreds and thousands of photos. And so you have all these digital photos on your computer, and it's very typical for an individual to amass, an amateur, not even someone trying to be a photographer, but it's very typical for someone to amass quite a large collection of photos in their photo library. And so let's say you have an enormous photo library, and you, with clustering, you arrange these photos into groups based on the content. And so maybe you do this clustering, and you end up with these three groupings, right? One grouping up here at the top, one here on the left-hand side, one here on the bottom, based on the content. And then once you go back in, you look at those groupings resulting from the clustering, and then you give them names. And so the name you ascribe to this one is, that's Yellow Lab, and maybe this one is the Pugs, which it is, and then this last group is the German Shepherd. So you analyze and name your groups. So in doing so, you're basically arranging your images based on the content, and it's automated, so it's easy to do. You run a piece of software that does it for you, and it's especially important if you have these huge image libraries consisting of many thousands of pictures. It's really hard over time and over the years to go through and look at each one of them. So that's why image clustering is useful. So let's take a look at images from different categories. Where do these images come from? Well, certainly you could take these pictures yourself. And if you're trying to do any kind of learning to do prediction of things on images, you need a very large number of images. So that begets the question of where you might get these images. Well, you get them from computer vision databases. So what is a computer vision database? So many researchers in computer vision often create and they share these databases full of lots and lots of images. And the idea with these image databases is to enable others to reproduce their results, because after all, they're trying to use standard sets of images in order to build these models which are useful, that are already trained, which will predict, hey, this is a dog, this is a cat, this is a desk, and so forth. And things have gotten quite good, especially with deep learning running on these image databases. So that's where you get these images. In fact, you don't even have to do prediction of what your images are. There are a lot of pre-trained models out there, classifiers, which will predict for you, and they're quite good. And the reason why they're quite good is because people have contributed these image databases. And so they're used, these databases, to benchmark certain algorithmic performance. It lowers the barrier to entry for doing research. So if you want to start getting your feet wet in doing computer vision research, and if you need a source of images, there are lots available in these computer vision databases. And it also facilitates solutions to important problems, like how do you detect a face? How do you fill in pixels when part of an image is missing, and things like that. And so this is an example of a face recognition data set. And oftentimes some of these data sets are under ideal conditions in a studio. So here in the first frame, you have a frontal face, and you notice the lighting is ambient and it's on a very neutral background. Well, the real world never looks like that, but nonetheless, we can identify certain points corresponding to patches of images that represent important things that are useful descriptors for someone's face. So certainly what distinguishes one's face from another are things like the hairline, the lips, maybe if there's facial hair, the nose, the eyes, and the relative position or relationship between these spatially. And so here, if we look at this wireframe draws an edge depicting relationships between nearby points. Now, oftentimes, some of these things are done under ideal conditions, but a group from University of Massachusetts Amherst, UMass Amherst, where I did my graduate work, has a solution for this with something called labeled faces in the wild. It's a data set, image database, that has faces that are in non-ideal locations, i.e. in the wild, out and about in society. And so that's also available and became a very important face image database because it represents more realistically what happens when you're trying to detect faces and recognize faces computationally. Okay, and so an example image database, a very popular one, is called the Caltech 256 data set. It's from Caltech, which is California Institute of Technology in Pasadena, California, I believe it is. And this database has a total of 30,607 images. But what makes it particularly interesting is that it has 256 different categories, all sorts of things, like musical instruments, like insects, like vehicles, and so forth. And so some examples of categories, you have 102 dog images, 84 giraffe images, 102 bear images among the 256 categories in the Caltech database. So it's quite interesting if you're interested in doing work in computer vision, tinkering on your own. There's a very good source. Caltech 256 is a very good source of images, and it's available for free. Because you can imagine if you wanted to construct a rich data set for tinkering with some of these computer vision algorithms, it would take you either a really long time to take these pictures yourself, or it would cost you a lot to buy if you're trying to buy stock images from these vendors of image content. Okay, so let's take a look at features. Now again, we have in our example, we were talking about a feature vector in 40 dimensions. The first 30 dimensions of this vector are your color descriptors, which are the concatenated bins of the histogram. And so you had the 10 bins of red, and you had the 10 bins of green, and then lastly you had 10 bins of blue. And you concatenated the histogram counts as the features, and then this last 10 feature positions in the 40 vector is 10 bins of edge angle that you got from your edge detector. And so this 40 vector is our appearance-based representation. And so here we might represent the giraffe's color using RGB color histograms concatenated in a 30 vector. And one of the questions you might ask is, well, what is the impact of increasing the bin count? So instead of 10 bins representing color per each color channel, what if you represented each color channel using 20 bins? Now, if you have 20 bins, that means you're going to have more fine-grained representation. But with these 20 bins for red, green, and blue, you collect these bin counts to form your feature vector, and now your color portion in your representation is now a 60 vector and no longer a 30 vector. So you're increasing the dimensionality of the color portion in that appearance-based feature representation. And so what happens when you have more bins? Well, if you have fewer bins, that represents a smaller range of colors. So that means that smaller variations in color are represented. And for the giraffe image, what that means is you're better able to distinguish among giraffe pigmentation. So maybe one giraffe might be light brown, one giraffe might be dark brown, one might be medium brown. Those are all considered different colors because they result in different counts in different bins in this representation. And that is afforded by the smaller range of values represented by that increased number of bins. And so that is more distinguishing. It's more fine-grained. You can more tease apart very minor or more minor variations in the color as you increase the number of bins. So what is the impact is for the converse if you have fewer bins? Well, if you had fewer bins, that would mean, for example, instead of having 10 bins per color channel for your histogram, you have 5 bins. And so that would be 5 bins for red, that would be 5 bins for green, that would be 5 bins for blue. So you collect them all together, that's a single 15 vector representing the color portion of your appearance-based feature instead of that 30 vector. And so what happens if you have fewer bins? Well, fewer bins means each bin represents a broader range of color values. And in essence, what this does is it collapses a broader range of pigmentations for the draft into a single representation. So the example we carried before, suppose you had drafts that were dark brown, light brown, and medium brown. Well, if you had fewer bins, that would just call it all brown instead of making that distinction. And so it's more coarse-grained in the representation because all of those variations would fall into the same bin. Okay, and so for the edge angles, we have a similar consideration when you're trying to represent your appearance-based features. We talked about this idea of the edge magnitude and the edge angle, and we can take that edge map and we can compute a histogram over it, say 10 bins, and get this 10 vector representing the shape information for portion of that appearance-based feature. And so here, what happens if you have more bins? Well, more bins means each bin represents a smaller range of angles. So that means smaller variations in edge angles are represented uniquely. So let's say if you had edge angles at 35 degrees, 45 degrees, 55 degrees, they're all considered as different shape measurements from an image. If you had fewer bins, well, the converse happens. That means fewer bins corresponds to each bin representing a broader range of edge angles. And for that, you're basically collapsing edge angles into a single descriptor. Right? So that would mean edges at angle 35, 45, and 55 degrees would all be just considered slanted. It's the same category or the same descriptor versus distinguishing more fine-grained. And so with each of these appearance-based features, when you use your histogram, you have to also consider the impact of whether or not you can use a smaller number of bins or a larger number of bins, because that's going to impact your representation and your ability to compare things when you're trying to arrange them into categories with your clustering. So here's an example. Suppose you have a baseball and you also have a picture of a house. Now, if you consider the edges for this baseball is round, and if we just kind of draw the contour edges, we have edges roughly at every orientation if you go around the edge of this baseball. And so round things tend to have a more uniform distribution over your edge angle. So if you use a larger number of bins, you're representing more fine-grained all the edges, and you're more likely to be successful describing things that are more rounded in shape. So let's say you have fewer bins. Well, let's take a look at this house. Now, if we look at this gable here for this house, I think that's what it's called, this gable. Engineered objects tend to have very straight edges, right? You don't have very often rounded things on buildings. I know that's kind of ironic, seeing this rounded window here for the skyline. But nonetheless, for the most part, for human engineered objects and structures, you tend to have more straight edges. And so here, if you had fewer bins, well, it distinguishes that, okay, well, engineered objects tend to have peaked distributions over edges, meaning you have a smaller number of orientations, and therefore you want to represent whether something is slanted or something is horizontal or something is vertical. And so having a smaller number of bins might be useful for representing objects in terms of the shape information for images, for representing things that are human engineered. And so you have a handful of dominant edge angles when you have human engineered objects in your image. And so for that, fewer bins might be more useful. All right. And so you can also, when you're thinking about shape features, you can have more sophistication in your representation. And so global shape takes all of the edges in your entire image. You compute the edge orientations, and you compute a histogram of those edge orientations. Now, that histogram measures the shape, or sometimes it's called the shapeness, or the global shape, because that corresponds to the distribution of edge angles for the entire image. Now, there's also, if we form a 10 vector from that, that's a global shape vector. There's also a notion of local shape. And in local shape, you take your image, you tessellate it, so you chop it up into pieces and divide your image up into cells, and then you compute the edge orientations for each cell. And so now you represent the histogram of edge orientations for each cell in some ordering. So maybe that's the first cell, the second cell, third cell, and so forth going across. You wrap around and then you go across in some orderly fashion, traversing through all the cells, representing the histogram of edge orientations for each cell. So with that, you would have, say, if you did 10 bins per histogram of edge orientations for each cell, you would have a cell for the first square here. If we chopped it up into 4 by 4 grid, you'd have 10 bins in the edge orientation histogram for the first one, second one, the third one, up through and including that last one, which is the 16th cell. So now you have 10 bins per cell for the histogram of edge angles representing the edge orientations, and we have 16 total of these cells. So that would be 16 times 10, resulting in a pretty large vector, 160 vector. And so with this, the dimensionality of the resulting shape information would be the number of cells times 10 bins. Now, certainly what this does, it pulls out edge orientations for regions of your image versus just throwing away all that relative position information. So in this particular case, your edges here would be the reflection of your edges here. And you know that they're next to one another. And this local shape information not only encodes the shape, but it also encodes the shape in different patches of image relative to other patches of image. So you have relative relationships for these edges, not just this global information. And so that is useful for all sorts of applications when you have local, and there are all sorts of variations on the scale between pure global and very local. Okay, and so there's a type of edge feature called HOG, or histogram of oriented gradients. And this is a very useful feature to use. And in fact, you'll be using them most likely in your implementation. So that's why we're talking about them. And I encourage you to use HOG features. So HOG features builds on this idea of local and global edge description, shape description. And so in HOG features, you have your image and you divide your image into cells. So these are the cells, are these small green blocks here. And then you take this thing called a block, and a block is some number of cells, m by n cells. In this case, we have the first block, which is red, it's 2 by 2, and then we have the second position of a block, which is also 2 by 2. And so you divide your image into cells, and those are the smaller squares, and then you define a block as being some m by n cells. Now, m doesn't have to equal n, which is the case here. It's 2 by 2. M can be different from n. So then what you do is you take your block and you slide these blocks to be overlapping to some degree across and down the image. So the block might have the first position here, block 1, and then next is block 2. You move over one cell, block 3, block 4, and so forth. And so you do this by sliding your block, and then you compute edge gradients for each cell within a block. Okay, so that means you take a block, and then you take your block, and your block is comprised in this case into 2 by 2 cells. So then you take a histogram of each cell for the edge orientation. So there's a histogram here, there's a histogram for this one, and there's a histogram for this one. Okay, so once you do that, you're going to use each of these histograms essentially in a voting mechanism. And so this voting mechanism, this histogram is represented here. You have 9 bins. And you've noticed here, these 9 bins are marked with angles. And so here we have 0 to 20 degrees, 20 degrees to 40, 40 to 60, 60 to 80, 80 to 100, and so forth, in 20-degree wedges here from 0 to 180 degrees. So you have these 9 bins spanning all the angles from 0 to 180, and then you take each cell's edges and you run this edge orientation histogram over each one of these cells. So you take your block, you take your cells, you do your edge extraction using your edge operator, and then you take each cell, you run it through this histogram, and then you get some number of bins here. You get 9 bins for each one of these cells, a histogram of 9 bins. So it's a 9 histogram. So now you let the cell in each block vote, right? And the cell in each block are going to vote based on the edge orientation, and it uses this histogram to vote. So each histogram of size 9 bins is going to vote among other cells within the block. And the biggest count then is going to win in terms of the orientation and the edge magnitude. So we have a histogram here for this one. We have a histogram here for this one. We have a histogram here for this one. And we have a histogram here for this one. So now you take each one of these and you're going to now vote, right? Which one has the biggest count for each one of these cells, right? And that's going to be the dominant orientation and magnitude as a result. And that's called Hogg feature. So here's an example of Hogg features, right? You compute these Hogg features for each one of these block positions voting, and you're going to end up with a winning histogram for the first position. And then you slide this block one position over or some number of positions over, and then you do that voting again. You get another one. And so if you do this for this entire image, well, you get all these votes that are happening, and the result of each vote is some winning histogram, as it were, each one of the bins for the 4 histograms in this case. And so then, if you do that across the entire image, this is an example of all of those resulting positions. So each one of these is a block position, and each one of these histograms here is the result of the cell histogram votes. Okay, and so you then take each one of these result of the cell histogram votes and you concatenate them, and this is your feature vector, right? And so the winning one is 9, so then you're going to have 9 bins per histogram, and the number of histograms that you're going to have across the whole image is going to be the number of block positions as you slide this block from one cell to the next. Now, of course, when you slide it, there are many ways you can slide it, and we often talk about the span and we talk about the overlap. Now, in this case, these blocks, when you move block from the position of block 1 to block 2, they overlap by 50% along X. Right? And so in the specification of Hogg features, when you use a Hogg feature operator, one of the things you specify is the amount of overlap as well as the size of the block and the number of cells. Okay, so let's take a look at an example of Hogg features. Now in this representation, we're plotting the dominant edge magnitude and orientation associated with the winning edge for each of these block positions. And so here we have an image of someone walking along a dock along the water side, and this is the resulting Hogg feature that was computed. And so here these edges look like they represent the ripples of the waves on the water. And then here we have the person walking. Well, let's see, the person's arms out at an angle, and we have edge out at an angle representing that person. We also have the side of this person's leg or hip, and we have there's hip here and here, and then we have the person's leg. Well, that's the person's leg. If we notice here, that silhouette, we have that exact silhouette here, representing that part of the person. And so when we notice here this edge of the jacket, that's particularly interesting. We see from the votes that edge is pretty dominating, and then we have this edge, which is pretty dominating. That edge looks like it's the edge here. And so you can see these edges emerge from the image from these Hogg features, and each one of these plots here represents the dominant edge associated with the block after that voting is done among all the cell histograms. Here's another image. Someone is standing, I believe, on a beach, and they have the arms extended, and you can see here the arms are at this angle, and we have another edge here. Well, we have an edge here, and we have another edge here. And then likewise here, when we have the jacket here coming in, well, we pick up that edge. We also have this portion coming out. We also pick up that edge. And so it's very interesting. We see the legs here. You see between the legs, we have that edge and that edge. You notice we have edge here, and then we also have this edge and the right hand edge. We have that edge, and the hand or arm is extended out at an orthogonal angle to the other one. And guess what? Lo and behold, we have it. And so this is precisely the set of dominant edges associated with this image. And so there's some URLs on the slide. Please check them out. It talks about Hogg features. Okay, and so histogram of oriented gradients, Hogg, it takes this idea of local shape descriptor and it makes it a lot more robust using this voting mechanism. Okay, and so it just so happens in MATLAB we have a hog feature API routine, extract hog features, and I'll leave it to you to investigate all of the parameters that you need to use it. But for this call, it's up to you, and it's part of your assignment to decide what the cell size is, the block size, the overlap, and the trade-off that arises between speed and efficiency. There's always a trade-off when you choose these parameters affecting the cell size, the block size, the overlap, and so forth. Okay, so that's the API call, and so you'll be using that on your assignment. And so what features and what data will we be using for the project? And so I've created a data set, and that data set has 4 different categories of dog. We have golden retrievers, we have chocolate Labrador retrievers, we have German shepherds, and we have border collies. And so there are 15 of each of these for a total 15 German shepherds, 15 of this, for a total of 60 images. And so what your goal is to design an appearance-based feature descriptor using both color and shape. So you get to decide using hog features and some color representation. And you're going to use 4 different categories for clustering. And these dogs are from 4 categories, and they're all on white backgrounds to simplify the problem. Okay, and so you have to first design an appearance-based feature descriptor, so that's using color and shape, that is suitable for the clustering task to arrange these 60 images into categories. And the hope is that if you do it appropriately, correctly, it's going to sort them out in terms of the actual breed. All right, and so when you perform k-means clustering, we talked about Lloyd's algorithm during the semester when we talked about clustering. We chose randomly a set of cluster centers, mu1 through mu k, and of course k here is going to be 4, but you could try it as 2, try it as 3, try it as 4, and maybe try it as more than 4. If you try it as more than 4, it's going to subdivide your categories, and maybe it'll be a certain type of German Shepherd instead of just German Shepherds. So then you take each one of your representations, xj, this is for a single image, so this is the J image, and that's going to be in D dimensions, and you decide how many dimensions because you're determining what the appearance-based feature is. So you randomly assign points to clusters, and then you minimize iteratively the following expression. You're saying, I want to make the individual clusters compact. So for every data point in a particular cluster, you want to minimize the magnitude, the squared, of the distance between that data point in the feature space and the cluster center. And you're going to do that across all of the big K, where big K is equal to 4 clusters, right? So that's the ideal. So what do? You start out with some initialization, and then you update the centers holding the cluster assignments fixed. So you fix cluster assignments. You do not change them, and you take the mean, right, the sample mean, over each of the features for all the data points in the cluster, and you update your cluster centers for each one of your clusters. Okay, so then after that, you hold the cluster centers fixed, so you fix cluster centers, muse, okay, and then you reassign each of the data points to a new cluster. And so what do? You say a particular data point, going through all of the data points, there are 60 of them in the data set, you reassign them to the kth cluster based on whether or not they're closest to that particular cluster center mu sub k. So if you're closer to the first cluster center mu1, a particular data point xn, then you're going to put that data point in cluster S1 in the first cluster. So you fix the cluster centers and you update the cluster assignments. So then you fix the cluster assignments, and conceivably that will have changed when you did the cluster reassignment for the clusters. You fix the cluster assignments, and then you update the cluster center, because the center would have changed if the cluster assignment has changed from this cluster reassignment step. And so you keep alternating between these two for some number of steps until convergence. And convergence means that there are no longer any changes to either the assignment or the cluster centers. Okay. And so we talked about Lloyd's algorithm when we discussed during the semester clustering. So for your assignment, you'll be using the MATLAB API call that implements Lloyd's algorithm, k-means, and I will leave it to you to look through the documentation now that you understand what Lloyd's algorithm is to choose appropriately what the parameter settings should be for MATLAB's k-means implementation, which is Lloyd's algorithm. And so what will you be deciding? The number of iterations of Lloyd's algorithm, how you initialize the cluster centers, what distance measure you use when you're trying to determine whether you're closest to a particular cluster center, right? That's going to impact your result. And then also the number of clusters. You might try the perfect 4 clusters knowing you have 4 breeds of dog in the data set, but you might also in your experiment, which is important to do, to try maybe 2 clusters to see which dogs it puts together, and then maybe more than 4 clusters to see which dogs it separates. So maybe there's a different type of German Shepherd that is grouping together. So subdividing those dogs into subgroups. And so your feature representation will certainly impact the performance because with a bigger feature representation, this computation of this distance measure is going to take longer. Okay. So it's up to you to decide what the right parameterization is, but the end result in the beginning is to try to get that clustering correct. Okay. And so next thing you do is, of course, you're running some experiments, you're going to examine the results. And so first of all, how did your algorithm perform? How well did it arrange those 60 images into their natural groupings? What were your clusters? What was the result of your clustering? What name would you assign to your grouping, right? Maybe it's the lighter German Shepherds. Maybe it's the spotted Border Collies. Maybe it's the less spotted Border Collies. What name would you assign to your grouping? And so you're going to be saving a lot of images based on your grouping. And how did the performance change as you modified certain experimental parameters? If you change the feature representation, your appearance-based feature, how did the performance of the clustering change? Not only just the runtime, but its ability to group things together and why. And so if the number of clusters change, what happens? If you increase the number of grouping, decrease the number of clusters or groupings. And what would you try or could you try to do in the future beyond this class if you wanted to further improve this? So that's knowing what you know as a result of your experiments for the final project. What would you change to try to improve this, or how might you improve it at a high level? Because certainly this would be the subject of a computer vision course and a machine learning course. We have 2 semesters, one of computer vision, one of machine learning. Okay, so in summary, what is your task? Your task is image clustering problem. You're going to input images across the 4 different categories, breeds of dogs, and the data I've supplied. You're going to implement appearance-based features. You're going to perform k-means clustering, Lloyd's algorithm using the MATLAB APIs, and then you're going to examine the result and try a bunch of different results and report on what you find. Okay, so with that, we will end there, and certainly that's it. That's it. The class is done. And so over the course of the semester, we've done a lot of things. We've talked about statistics. We've talked about inference. We looked at various proofs for consistency and bias. We looked at clustering. We looked at classification. We looked at parameter estimation using max likelihood method of moments. We looked at appearance-based features. We looked at regression. We looked at classification. Looked at the pseudo-inverse. We looked at the perceptron learning algorithm. We looked at hypothesis testing and confidence intervals. We looked at the Z distribution. We looked at all sorts of things. And so with that, I hope this course was a benefit to you. And I thank you for taking the course. And I understand it's a required course, but nonetheless, I thank you anyways. I appreciate all of your hard work, particularly since after spring break, we've all been sheltering in place, taking this purely online, and I fully appreciate and thank you for all of your hard work continuing on amidst this suboptimal situation as we get through this COVID-19 pandemic. And so with that, I hope it's beneficial to your careers. There are certainly alumni of this course who are using it directly in their jobs. I'm happy to chat with you about that offline. And so hopefully now it's given you enough tools in your tool belt to give you a very solid understanding of data analytics so you can go off into the world and prosper with this material. And I would be absolutely thrilled if all of you, or many of you, had a job that involved data analytics, and more and more and more as data increasingly pervades just about every industry out there, you're going to have to understand data analytics to some degree. And so I like to end with this meme. I'm a fan of internet memes. This is how I hope you walk after your last lecture in data analytics. Put a little bit more strut in your walk as it pertains to your analytical ability. So with that, thank you. It's been a great semester, and I look forward to your final projects. As always, please stay safe and stay healthy. Take care.